Radiation heat transfer, real surface behavior. Okay, so if you're a first-year chemical engineering student, you've learned all about ideal black bodies. But in the real world, when you're designing something like a reactor, materials behave very differently. And understanding that is absolutely crucial. First, real surfaces are not perfectly diffuse. This just means the direction of the emitted radiation actually matters, a concept we call directional emittance. For example, electric conductors, like polished nickel, tend to emit more energy toward the edge, so a glowing sphere of it would look brighter around the rim. Non-conductors, like wood or glass, do the exact opposite. They appear brightest right in the center. Second, most real surfaces aren't what we call gray bodies, but we often treat them that way to make the math simpler. A true gray body has a constant emissivity and absorptivity across all wavelengths, which is based on Kirchhoff's law. Now, while real surfaces deviate from this a lot, the gray body assumption simplifies the analysis so much that the ease of calculation often justifies the small error. Finally, let's talk about geometry. We use what are called radiation shape factors, or view factors, to figure out heat exchange. A shape factor is really just the fraction of radiation that leaves one surface and actually intercepts another. So instead of always using complex integral formulas, we can rely on foundational rules, like the summation rule and reciprocity relations, to find unknown factors for all sorts of complex designs. Let's dive into more detail.
Hey everyone, if you're in chemical engineering, you already know that heat transfer is, well, everywhere. But there's one mode, radiation, that can sometimes feel a little abstract. Today, we're going to fix that. We're going to pull back the curtain on radiation heat transfer and show you exactly how those textbook principles become real, practical tools you'll actually use. Okay, so let's just jump right in with a question that, I gotta admit, completely stumped me the first time I saw it. You've got two spheres. They're both heated up until they're glowing red hot. You'd think they'd look pretty much the same, right? Well, they don't. And understanding why is the key to unlocking a really fundamental concept about how radiation works in the real world. So check this out. On the left, you've got an electrical conductor. Think of something like polished metal. See how it's glowing brightest right around the edges, around the rim? Now look at the sphere on the right. That one's an electrical non-conductor, like a piece of glass or ceramic. It's the total opposite. It's brightest smack dab in the center and gets darker toward the edge. So what on earth is going on here? The answer, it turns out, is in this really fascinating gap between the ideal, simplified models we learn about first and how real surfaces actually behave. And this isn't just some cool visual trick. It's the perfect example of why material properties are so incredibly important in any kind of thermal design. In your classes, you probably started with these ideal diffuse surfaces, and it's a really useful simplification. The idea is that an object radiates energy perfectly evenly in every single direction, kind of like a tiny, perfect light bulb, sending out light uniformly all around it. But as we just saw with our glowing spheres, the real world is a lot more specific and honestly, a lot more interesting. So how do we actually capture this real-world behavior with numbers? The key is a property called directional emissivity. It's basically a measure of how much energy a surface sends out at a specific angle. So think of 0 degrees as being straight off the surface and 90 degrees as being perfectly sideways, parallel to it. And what's wild is when you plot this for different materials, you see they split into two very, very distinct groups. Okay, so we've nailed down that what a thing is made of is crucial. But what happens when you have more than one object and they're all radiating energy at each other? Well, then the physical layout, the geometry of the system becomes just as important. To deal with this, engineers have this incredibly elegant tool. It's called the radiation shape factor. You'll also hear it called the view factor, which is a great name for it. The definition is so simple but so powerful. It's just the fraction of all the radiation that leaves one surface, let's say surface I, that hits another surface, J, directly. The shape factor is always just a number between 0 and 1, so if surface J can't see surface I at all, the shape factor is 0. If J completely surrounds I, it's 1, and the key thing is it's a purely geometric property. It has nothing to do with temperature or material. A great way to think about it is to just ask, from the point of view of surface 1, how much of my view is blocked by surface 2? All right, so let's see how we take this idea and turn it into a practical toolkit. We're going to look at how an engineer takes a real physical setup, figures out its shape factor, and then uses that number to calculate the actual amount of heat being transferred. We're going to zero in on this very common setup. two rectangular plates that meet at a 90-degree angle and share an edge. You can picture this all over the place, right? Like the floor and a wall in a room, or two sides of a furnace. The question is, how do we find the shape factor between surface 1 and surface 2? Now, you could look it up on a chart, or you could go right to the source formula. And I know what you're thinking. That equation looks like an absolute monster. But trust me, let's walk through it. Every single piece is just telling the story of the geometry. That 1 over pi w term out front, that's a scaling factor based on the area. The arctangent parts, that's just the math way of describing the angles that the edges of the plates make from each other's point of view. And those more complicated terms with the square roots, they're just precisely accounting for how the view from one plate to the other changes as you move across their surfaces. It's really just a perfect, self-contained description of the physical shape. So here's the really beautiful part. That entire intimidating formula, it all boils down to just two simple, dimensionless ratios. H is just the height of the vertical plate, z, divided by the length of the edge they share, x. And W is the width of the horizontal plate, y, divided by that same shared edge length, x. You just calculate these two simple numbers from your system, plug them in, and you've completely solved the geometry part of the problem. All right, enough theory. Let's put this into action. We're going to take a classic problem and go through the exact steps an engineer would to turn geometry and temperatures into a real number, a number with units of power. So here's our setup. Two parallel plates, a slightly different geometry, but the process is exactly the same. They're called black plates, which is just engineer speak for a perfect emitter, 100% efficient. One plate is at a blistering 1,000 degrees Celsius, the other at 500. So step 1, we calculate our dimensionless ratios based on the side lengths and the distance between them. Step 2, we take those ratios to a pre-calculated chart and find our shape factor, which turns out to be 0.285. All that means is that 28.5% of the energy leaving plate 1 goes and hits plate 2 directly. Finally, we plug that shape factor into the main equation for radiation heat exchange. And what do we get? The answer is 18.33 kilowatts. Just think about that for a second. That's enough energy to run more than a dozen houses, all being transferred silently, invisibly, between two metal plates just through pure radiation. And that is the real payoff, right? We took this abstract geometric idea, the shape factor, and used it like a bridge to calculate a real, tangible, physical amount of energy. This is what engineering is all about, using these powerful abstract tools to predict and control the physical world around us. Now, like with any powerful engineering tool, it's really important to understand the assumptions we made along the way to get that nice, clean answer. A huge part of being a good engineer is knowing which simplifications are smart and which ones might get you into trouble. So in that last example, remember, we assumed the plates were black bodies, perfect 100% emitters. In most real-world problems, we use what's called a gray body assumption. That just means we treat the emissivity as a constant value that's less than 1, say 80% or 0.8, and assume it doesn't change with temperature. As the textbook says, trying to model every single tiny variation of a real surface is just insanely complicated. The gray body assumption is a practical trade-off that gets us answers that are more than good enough for most real-world designs. And what happens if the geometry you're working with isn't on one of those nice standard charts? Well, for more complex shapes, you don't always have to go back to that monster integral formula. You can use something called shape factor algebra. It's a cool trick that lets you figure out an unknown shape factor by adding or subtracting known ones. You can basically treat them like geometric building blocks to build the exact shape you need. So today, we've gone from a simple, curious observation about a glowing sphere all the way to calculating actual kilowatts of power. And everything we covered, from understanding how a material's properties change what we see, to using the shape factor to nail down geometry, these are the absolute fundamental building blocks. And it leaves us with one last thought. Now that you have these tools, how would you start to analyze something really complex, like the inside of a furnace or a rocket engine? You'd start exactly the same way, by identifying the key surfaces, estimating their properties, and calculating the shape factors between them. The principles are always the same.